All right, people. So we're going to talk about chemistry and then how it originated. All right. So first thing, um, early chemistry, early history of chemistry. Now, chemistry, the idea of the atom, goes back to about 1000 BC with a philosopher, a Greek philosopher called Democritus. Democritus was a philosopher. He did no experiments, so this is all thoughts. Like, when you question your existence in the universe, or you question just the world around you. So one thing he thought about, well, what happens? What are we made out of? What are we made out of? What are things made out of? Let's take a sheet of paper, for example. If you take a sheet of paper and you cut it in half, it gets smaller. And then you cut that in half, it gets smaller. And you keep cutting it in half and half and half and half. Eventually, you're going to reach a point where you cannot cut it anymore. It's going to be very, very hard to cut. He called that an atom. He said, or atomos, meaning indivisible, not able to break apart. And what he, that thought was an explanation to everything around us. Everything was made out of a particle of itself that couldn't break apart. So papers were paper atoms. Papers had paper atoms. Leaves had leaf atoms. Trees had tree atoms. Right? Whatever. It had a smaller version of itself that nothing can break apart. Like a very, very tiny speck of dust. Now, he wasn't the most prominent philosopher at the time. At the time, there was Socrates. Or not Socrates. Aristotle. And Aristotle had the belief of the four elements. The Avatar, the Last Airbender one. The earth, wind, water, and fire. All four nations lived in harmony till the Fire Nation attacked. Right? So Aristotle's view was things are made out of a mixture of those four. For example, mud is earth and water. Steam is wind, water, and fire. Fog is wind and water. And things were just a combination of that. So that was the most widely accepted idea. Wrong. Now, let's go a little bit further in history. Let's go to 700 AD. 700 AD, there was Jabir. His name was Jabir ibn Hayyan. He was an alchemist. And a philosopher as well. He was one of the first documented to actually perform experiments and write down his experiments. He isolated and created a few chemicals himself. He made hydrochloric acid, nitric acid, aqua regia, which is a mixture of two acids that can dissolve gold. So he was one of the first documented experimental scientists, but he did not write down his methods of calculations. Alchemy was more secretive, so they wouldn't share secrets or wouldn't publish the secrets or create falsified information in case anyone wanted to steal it. So alchemy during that time was very hush-hush, and it's my stuff because it's going to make me rich. Later on, when we talked, later on in history, Robert Boyle and Antoine Lavoisier, they were European scientists, and this was around the 1600s. And both of them created the fundamentals of chemistry that we know today, where all data is accurately measured and experiments are designed to be as isolating as possible. So Robert Boyle was one of the first to document experimental data and use that to explain nature. So he measured the relationship between pressure and volume of a gas, and he wrote down his values and he compared them in a graph. So he used data from the experiments and then tried to explain the data. Antoine Lavoisier did the same thing. Oh, sorry, a word you need to know: quantitative. That N, think of number. Quantitative means a quantitative experiment is an experiment that relies on data. Qualitative experiment is just something you rely on. Does it look? How does it look? For example, you can test for oxygen with a candle. If the candle goes out, no oxygen. If the candle burns bright, there's oxygen. That's a qualitative experiment. Quantitative, you write down numbers, you collect data. All right, so Robert Boyle, really good at creating data, kind of set the bar there. Antoine Lavoisier, around the same time, did the same thing, but he was very, very meticulous. One thing Antoine Lavoisier did was he set up his experiment so that he can measure the experiment before it started and after it had gone to completion. So he compared it in the beginning, he compared it in the end, and he found out that the mass never changes. The mass stays the same. So he came up with the law of conservation of mass. Mass is not created and it's not destroyed. One thing Antoine Lavoisier did, well, he did a bunch of things. He isolated a bunch of chemicals. If you do a project on him, any extra credit. Antoine Lavoisier, he discovered oxygen. He isolated oxygen. He explained combustion. He is the reason why we understand combustion. He is one of the reasons that eventually led to the Industrial Revolution, because you can, if you understand how combustion works, you can learn how to maximize it, make it more efficient. A lot of other people in the book also contributed to that. We'll talk about that when we get to thermochemistry or thermodynamics, or both. All right. Now, another guy, I forget his first name, but Proust, I think he's French. Proust, he came up with something called the law of definite proportions. Now, these chemists, the way they did it, the way they would perform experiments without knowing what would happen. They would just measure what would happen. They would measure what would happen, and then they would try to come up with a reason for why the data changes. So, for example, if we look at some of the problems here from the work, we're going to do just that. All right. Now, this type of problem is it's based off the law of multiple proportions, or definite proportions. The law of definite proportions basically said, like, let's say, imagine we have this compound, CuSO4, copper sulfate, or I have the values written down here. They are, let's say copper carbonate, CuCO3. CuCO3. Now, if you had, let's say 10 grams of copper carbonate, or if you had 1,000 grams of copper carbonate, what the law of definite proportion said was that the percentage of each element is going to be the same regardless of how much mass you have. So, for example, the percent by mass, this one tells us that it's going to be 5.3 parts copper. It's going to be 4 parts oxygen. Or 4 parts oxygen, just O. And then how many parts of, I should have had this right now, on 1 part carbon. Sorry for my ugly writing. So basically it was a 5.3 to 4 to 1 ratio, regardless of how much you had. It was always the same value. And this law of definite proportions applies to everything. So that regardless about the quantity, the amount of the elements is always going to be the same. All right. Now, how do you come up with that conclusion? Well, that's the law of definite proportions. Now, Then Dalton went on to come up with the law of multiple proportions. And what he's saying was that, this is a very funky one to explain. We're going to do this one over here, this law of multiple proportions. We're going to explain it just a bit with, because these are what a lot of your problems will look like. I don't want to lose you, or so you can have a quick reference point later on, okay? So I'll end the video here. See you later.